Hello! Today we're going to be talking about continuity. In order for a function to be continuous at a particular point, it has to satisfy three conditions. The first one is that the limit must exist at the point you're trying to show it's continuous. And we accomplish this by showing that the left and the right-hand limits equal. We also need to show that the function actually exists at the value for x. But this one's really easy. All we have to do is prove that there's an output when we plug in whatever value it is for x. Or, if you're looking at a graph, just show that there's a closed dot somewhere at x equals whatever. Finally, we have to show that the limit equals this output. Basically, what we're trying to prove here is that our destination, whatever the limit equals, is the same as where we actually end up, the y value when you plug in your value for x. And that's it for conditions. Now let's take a look at the different types of discontinuities we get when our different conditions fail. Well, since the first condition has to do with limits, why don't we talk about what happens when the limit doesn't exist? No matter what, if the limit doesn't exist, this means you either have a vertical asymptote, which we'll call an infinite discontinuity, or a jump discontinuity. We'll take a look at what that looks like on a graph in just a minute. Next, we want to know what happens when the function doesn't exist. This means that the value for x is not in the domain of your function. Now, if there aren't any other points around this value that also aren't in the domain, then what we have is a removable discontinuity without replacement. This will result in a hole in the graph, and we usually have these when we have rational functions. Now, what happens when the limit exists and the function exists, but they don't equal each other? We get something that looks kind of unusual. We produce a hole in the graph with a point directly above or below this hole. We call it a removable discontinuity with replacement. It's like a hole in the graph that we filled in somewhere else. Okay, I think we're ready for some problems. Let's take a look. In our first example here, we have a graph of a function, and we're asked to determine if the function is continuous at x equals 3. Clearly, we have a jump discontinuity at this point. But we can't just say that, we have to prove it rigorously. Remember, we have a jump discontinuity when the limit doesn't exist, so to show that, we're going to have to show that the left and the right-hand limits don't equal. Okay, so here's x equals 3, straighten that out a little bit. Let's figure out what the limit is as x approaches from the left-hand side. Now, in problems like this, communication is going to be key, so make sure you're not lazy with your limit statements. The limit of f of x as x approaches 3 from the left is going to equal whatever our y value is. Here it's 2. Aha! Now we're going to repeat this process, but we're talking about as x approaches 3 from the right, which will signify with a plus sign next to our 3. This time our y value is 4, so the limit as x approaches from the right is equal to 4. These two values aren't the same, so we have to say that the limit does not exist at this point. And since nothing in math would be complete without some kind of concluding statement, what we have to say is that since the limit of f of x as x approaches 3 from the left, oh, little typo there, does not equal. The limit as x approaches 3 from the right, we have to say that the limit of f of x as x approaches 3 just does not exist. And you know what that means? It means that f of x is not continuous. There we go. At x equals 3. Good God. That's it. Let's move on to the next example. Alright, moving on, we have a piecewise function here. F of x is equal to 3x plus 4 when x is less than negative 1, 0 when x is negative 1, and x squared plus 2x plus 2 when x is greater than negative 1. And we want to show that this thing is or is not continuous at x equals negative 1. Now, the first thing we usually want to check with a piecewise function is whether or not the limit exists, because in these situations, lots of times we get jump discontinuities. We'll use the different pieces as x approaches from different sides. The top piece, or less than negative 1, is going to tell us what happens as x approaches from the left. The bottom piece, or when x is greater than negative 1, is going to tell us what happens when we approach from the right. And this piece right here gives us a nice handy piece of information. This tells us that f of negative 1 equals 0, which means that the function exists at this point. So let's go ahead and find this limit. The limit as f of x approaches negative 1 from the left is 3 times negative 1 plus 4. So we're plugging into this left-hand equation here. We get negative 3 plus 4, and that gives us positive 1. Now we have to check from the right-hand side. The limit of f of x as x approaches negative 1 from the right is going to equal negative 1 squared plus 2 times negative 1 plus 2. Very good. This is going to be 1 minus 2 plus 2, and at the end of the day, we get 1. Now, our left and our right-hand limits did equal each other, so that means that the limit of f of x as x approaches negative 1 does indeed exist. And guess what it equals? And it equals 1. All right. Well, we just found out that the limit equals 1, but we also found earlier that the function itself is equal to 0 when x is negative 1. So we conclude that since the limit of f of x as x approaches negative 1 does not equal f of negative 1, the function f of x is not continuous. Oh, we got to be specific about where, so we're just going to say at x equals negative 1. Boom. Easy stuff, right? Now, just in case you're curious, remember this means that both of our first two conditions are met, but our third is not. So what we're going to have is a removable discontinuity with replacement. So there's going to be a hole in the graph with a dot above or below. And I guess if you're paying attention here, since the value of the function actually equals at negative 1 is less than what the limit approaches, we're going to have a dot that's going to be beneath where the curve is. Alright folks, let's wrap this up. Remember the 3 conditions for continuity. The limit has to exist, which means that the left and the right hand limit have to equal like in this last example here. The function has to exist, which means you have to have some output when you plug in your interested value for x, and then the limit and the function have to equal each other. If all 3 of those things are met, then your function is continuous at your value for x. See ya!